Hi, this is Mrs. LaBarbera. This is Regents Physics, Chapter 7, Work, Power, and Energy, Video 8. Today's topic is Work Energy Principle Special Case, Ideal Mechanical System. Objectives are: know the definition of an ideal mechanical system. Understand, in an ideal mechanical system, total mechanical energy of the system can change from one form to another but remains constant. Another word means total mechanical energy is conserved. Be able to identify if a system is an ideal mechanical system, and be able to determine the changing potential kinetic in a system in which height or speed changes. An ideal mechanical system is a closed system in which there is no friction and there is no applied force acting on the system. So the only force doing work can be gravity or force of springs or both. So in an ideal mechanical system, total mechanical energy remains constant. This is why this is work energy principle in general. In ideal mechanical system, work by external force equals to 0 because there's no applied force and Q equals to 0. So that means delta P plus delta Ke equals to 0. So there is no change. If there is no change, the total mechanical energy has to be constant. So initial total mechanical energy equals final total mechanical energy. We can rewrite this as delta Ke equals negative delta P. What does this say? Is energy gaining in kinetic form equals energy lost in potential form, or vice versa. They are constantly changing from kinetic to potential and back to kinetic. Ideal mechanical system examples. First one is skiing. Think about during your skiing, friction can be ignored. Also, when you're skiing, the only force doing work is gravity because the other force is normal force. But remember, normal force is always perpendicular to the displacement. So normal force doesn't do any work. The system is ideal. TME is constant. Energy only transforms from one to another, kinetic to potential and vice versa. Another example is pendulum. Pendulum, if we ignore air resistance, TME is also constant. Why is that? Because the only force that's doing work is gravity. The other force is tension. Again, tension is similar to normal force in the way that tension is perpendicular to displacement. So tension doesn't do any work, just like normal force doesn't do any work. Another example is roller coaster. In the roller coaster case, it's actually very similar to skiing. You're just along a surface going up and down, back and forth, constantly changing the forms of energy from kinetic to potential and back to kinetic, then to potential and so forth. Another example is free fall. Free fall, in this case, free fall means free of air resistance. So the only force acting on a free falling object is gravity. Projectile is another case of free falling, right? So in this case, TME is also constant. And example number 5 is pop-up toy or a wind-up toy. In a pop-up toy, basically you press the toy down, the toy has a spring. When you press it down, you store the energy in the spring. Then when you release your hand, the toy is going to pop up. So what essentially happened is the energy in the spring is converted into gravitational potential energy, popped up. Sometimes you can have a wind-up toy. Wind-up toy is you're trying to store the energy in the spring by winding the toy. Then when you release it, that toy will start to move. So the energy is converted from from elastic potential to kinetic. Now let's take a look at the energy graph of free-falling object. The graph shows a ball is dropped. As a ball is dropped, its energy is transformed, how it's transforming. So this dotted line indicates gravitational potential energy right over here. As the ball is dropped, its position is getting lower and lower. Therefore, its gravitational potential energy is decreasing. But as the ball going lower and lower, its velocity is increasing. So as a result, its kinetic energy is increasing. The total energy is constant because this is an ideal mechanical system. Total energy is constant, is a straight line. Let's take a look at this example. So a pendulum is put to the side and released from rest. Sketch a graph best represent relationship between gravitational potential energy of the pendulum and its displacement from its point of release. So this actually question has nothing to do with energy conservation, but is more to do with gravitational potential energy. How do you define gravitational potential energy? Gravitational potential energy equals mg delta H. So at A, delta H is high. So you should have high potential energy. At B, delta H is low, so you should have low potential energy. Then comes to high again. So your graph should look very much like this arc here. Another example. In the diagram, an ideal pendulum is released from point A, swings freely through to point B. Compared to the kinetic energy at A, what is its potential energy at B? So this is again is not so much as conservation of mechanical energy, but you need to understand what is kinetic energy and what is potential energy. Well, kinetic energy is energy of motion. At A, it is at rest. So kinetic energy at A is 0. Potential energy, gravitational potential energy is related to its height. At B, it is at its lowest position, so its gravitational potential energy is also 0. So kinetic is 0, gravitational potential energy is 0. So in this case, they are the same. The answer is kinetic energy at A equals to gravitational potential energy at B. Okay, here is an example of ideal system. So 3 kilogram object is placed on a frictionless track at point A and released from rest. Assume the gravitational potential energy of the system to be 0 at point C. Calculate kinetic energy of the object at B. So this is an ideal mechanical system, so total mechanical energy is conserved. Energy at A, kinetic plus potential equals energy at B, kinetic plus potential. Kinetic at A is 0. Kinetic energy, potential energy at A is mg delta H. Delta H is 3. Kinetic energy at B is the one you have to find out. And potential energy at B is mg times delta H at B, which is 1. So you can solve this KEF equals 59 joules. You can also use the equation of changing kinetic equals negative changing potential. You will have the same thing. This really means when the object goes from A to B, it will lose potential energy because it's getting lower and lower. And where did potential energy go? It changed into kinetic energy. Okay, another example. The diagram represents a 0.2 kilogram sphere moving to the right along a section of a frictionless surface. Frictionless surface, ideal system. The speed of the sphere at A is 3 meters per second, right over here. What is how much kinetic energy does the sphere gain as it goes from A to B? The energy sphere gained is delta KE. Delta KE equals to negative delta PE. You probably say, really? Then don't I use 3 meters per second? No, actually you don't. You don't need that information at all. So this is one thing a little bit tricky. In physics, you'll have to pick out the information you need. You don't need everything. So sometimes they are giving you extra information. They are testing you if you actually understand the concept. Only by understanding the concept, understanding the kinetic energy gain is delta KE, you should be figure out this information is not used for you in solving this kinetic energy gain. So delta KE equals negative delta PE equals to negative mg delta H. Delta H is final height minus initial height. So you have 2 joules. Another example, base your answer to the question and on the information and diagram. A 250 kilogram car is initially at rest at point A on a roller coaster track. The car carries 75 kilogram passenger and is 20 meters above the ground at point A. Neglect friction. So again, when you see that indicates the system is an ideal system because there is no applied force. Calculate the speed of the car and the car and the passenger at B. So ideal system, total energy is conserved, total mechanical energy is conserved. PEI is mg delta H, KEI is 0. PF at B equals 0, what is the velocity at B? So MGHM is the two add together. 250 plus 75, you have 325 times G. Delta H is 20. Initial kinetic energy equals 0. Final potential equals 0 plus 1/2 m times V at B squared. So you can solve for VB equals to 20 meters per second. As a matter of fact, in this case, it doesn't matter what the mass is because they cancel out. So VB equals to 20 meters per second. Here is another example. The diagram shows a 0.1 kilogram apple attached to a branch of a tree 2 meters above a spring on the ground below. The apple falls and hits the spring, compressing it 0.1 meters from its rest position. If all of the gravitational potential energy of the apple on the tree is transferred to the spring when it is compressed, what is the spring constant of this spring? So that means this is what it means. All the gravitational potential energy is transferred to kinetic energy, to the energy in the spring. So you set up this equation. That's what this sentence means. You substitute what is given to you. Now over here, I have 2.1 meters. Why do I have 2.1 meters? Because the apple was 2 meters above the spring before it's compressed. When it's compressed, it will go lower 0.1 meters. So the gravitational potential energy relative to when it's compressed is 2.1 meters, not 2 meters. That should be equals to 1/2 K times 0.1 meter squared. And your solve for K is 412 newtons per meter. That's it for today. Thank you for watching.